Okay, now let's look at complex power. And complex power is really the way we want to calculate AC power, because complex power allows us, in effect, to simply use the phasor voltage and the phasor current that we're already familiar with. And along with that, we're also going to look at the concept of reactive power, which applies to inductors and capacitors. So here's where we begin. We know that P, which is equal to the average power, which we've already derived, is equal to Vm Im over 2 times cosine theta sub V minus theta sub I. So we've already established this relationship. We derived this before. Well, if you think about this, this is a cosine term, and we can always think of the cosine as the real portion of a complex number. So let's rewrite this. Let's say this is actually equal to Vm Im over 2 times the real portion of e to the j theta sub V minus theta sub I. So this is the real portion of this complex number, that cosine theta sub V minus theta sub I. That's simply the real portion of that number. All right, let's break this up. This is equal to 1/2, and let's take the Vm and the Im, and let's factor them into this real portion and write this like so. This is Vm times e to the j theta sub V times Im e to the minus j theta sub I. So all I've done is I've taken the Vm and the Im, I brought them in here, and I have decomposed that exponential term and written this like so. Except now that I've written it this way, this is Vm e to the j theta sub V. Then this is nothing but a voltage phasor. And what is this? Im e to the minus j theta sub I. This is the complex conjugate of a current phasor. We are flipping the sign on the phase angle. So what we find then is, really what we have is this is equal to 1/2 times the real portion of V times I complex conjugate. So that's what real power is. Real power is simply the real portion of that product, V times I complex conjugate. Well, given this, what if I were to go ahead and simply define a term using both the real and the imaginary parts of that V times I complex conjugate? Let's do that. Let's define a new term. We define complex power and in this case, I'm going to represent that as S. S is simply equal to 1/2 V times I complex conjugate. This is a definition we're going to use from now on for calculating power. All right? Let's take this for a moment. Let's do a little math to this. I'm going to take this and express this with these phasors in polar form. So I'm going to rewrite this and say that this must be equal to 1/2 times Vm theta sub V times Im minus theta sub I. So all I'm doing is I'm simply writing these two phasors as the magnitude and the phase angle, the complex conjugate, magnitude, and the negative of the phase angle. And now that I've done that, let's combine terms. This is 1/2 times Vm Im times theta sub V minus theta sub I. Now that I've got this, let me turn this into a rectangular form phasor. This is 1/2 times Vm Im times cosine theta sub V minus theta sub I plus j times 1/2 times Vm Im times sine theta sub V minus theta sub I. Now if we look at this, we recognize that term. This is P. That is the average or real power. So this is equal to P, but I've also got this term over here, J times 1/2 Vm Im sine theta sub V minus theta sub I. I'm going to define this term as Q. And Q is equal to 1/2 Vm Im times sine theta sub V minus theta sub I. And we call that the reactive power. Now, reactive power does not have units of watts. As we're going to see, reactive power only refers to the transfer of energy into and out of inductors and capacitors. And so we're going to give this units of VARs, volt ampere reactive. So reactive power has units of VARs. Now, reactive power specifically is a measure of how much power is absorbed and then returned to the circuit by an inductor or a capacitor. So reactive power is a measure of the amount of power absorbed and then returned by an inductor or capacitor when it's in a circuit. Q is not dissipated. And that's why we have the different units. Average or real power, P, is dissipated. This is not. Now, we note, given this definition up here, for a resistor, theta sub V and theta sub I are the same. Sine of 0 degrees is 0. So for a resistor, for any resistor, Q is equal to 0. In other words, resistors do not absorb and then store energy and then release it again. All they do is they dissipate it. So resistors have P. They have real or average power, but they have 0 reactive power. For a capacitor or inductor, you're going to have sine of plus or minus 90 degrees, which means that for an inductor, Q will be positive, since theta sub V minus theta sub I is equal to 90 degrees. For a capacitor, Q is going to be a negative number, since theta sub V minus theta sub I is minus 90 degrees. So this kind of leads to sort of a thing you can always remember. All right? Inductors have a positive reactance. In other words, inductors, when you calculate the impedance of an inductor, it's always a positive number. It's plus J something. And inductors also have positive VARs. Capacitors, on the other hand, have a negative reactance. In other words, the impedance always has a negative number, minus J some value. And they will have negative VARs. Along the same line, an inductor, theta sub V minus theta sub I is plus 90 degrees, positive reactance, positive VARs. A capacitor, theta sub V minus theta sub I is minus 90 degrees, negative reactance, negative VARs. So those signs carry all the way across. All right? Exactly what does it mean when I say that this is positive and this is negative? Because really, both the inductor and the capacitor are absorbing and releasing energy. So what do those different signs really mean? Well, they do have a meaning. The opposite signs indicate that when an inductor and capacitor are connected to the same source, then the negative signs or the opposite signs mean that if they're connected to the same source, when the inductor is absorbing energy, the capacitor is releasing it, and vice versa. So in other words, capacitors and inductors do the same thing. They both absorb and release energy, but they do it opposite of each other. When the inductor is absorbing, the capacitor is releasing. When the inductor is releasing, the capacitor is absorbing. So they're always essentially operating out of phase with each other. And that's what these positive and negative values for Q indicate for our reactive power. All right? Now that we've looked at the definition for complex power, let's apply it to a problem. Let's see how it works. And here's where you see the real value in the complex power equation, because it makes things very, very simple. And I'm going to use the same example that we did previously, this particular circuit. So once again, I've got a load impedance, Z sub L, and that's connected across this circuit. Let's calculate the complex power of that load. So in this case, this is 150 volts in rectangular form. I'm going to define a current, phasor current I sub L flowing into that load. And Z sub L, well, clearly Z sub L is just equal to these two impedances in parallel added to that one. And so just doing simple reduction here, this is J250 plus minus J75 in parallel with 100. And if I calculate this, what I'm going to get is this is equal to 36 plus J202 ohms. I sub L is therefore going to be equal to 150 divided by 50 plus Z sub L. So there's my I sub L. Once again, I calculate this. I will get 0.2676 minus J 0.6286 amps. Now let's apply the complex power equation. So in this case, S is equal to 1/2 times VL times IL complex conjugate. Well, I need to define VL across this load. So I need both the voltage and the current. What's VL? VL is equal to IL times ZL. We've calculated both of those. And that will be equal to 136.62 plus J 31.43 volts. And therefore, S, actually I should call this S sub L, the complex power of the load. So I'll use that nomenclature. S sub L is therefore going to be equal to 1/2 times 136.62 plus J 31.43 multiplied times the complex conjugate of L, which is 0.2676 plus J 0.6286. So in this case, I flip the sign on the imaginary part to generate the complex conjugate. And I multiply that through, and it will be equal to 8.4 plus J 47.1. Now, note the units. The real part has units of watts. The reactive part has units of VARs. Different units. I can't really combine those units together, so I give complex power a different set of units. I'm just going to call it volt amperes, VA. So when you write complex power as a complex number, you're going to use volt amperes, because what you're showing is it's combining both watts and VARs, both real and reactive power. All right. Note the 8.4 watts. This is exactly the same answer we got before when we calculated the real power of the load. Only then we found the phasor voltage across this resistor in order to calculate that. Well, now it just drops right out of the complex power function. And in addition, I also know the total reactive power due to those two reactive components, the inductor and the capacitor. Everything is there. So the complex power equation solves everything at once. This is the equation you want to use to solve for AC power. Makes everything very easy, and you're doing nothing but simply using the phasors you've already calculated using phasor analysis. Now, we can go one further step with this. Last time we talked about the definition for effective or RMS values. Let's define some RMS phasors. We note we can define VRMS, which is equal to an RMS magnitude theta sub V. We can calculate or define IRMS, which is an RMS magnitude theta sub I. So we can define these as phasors, as RMS phasors, and if we do that, then what we get is this is actually equal to Vm over the square root of 2 at a phase angle of theta sub V. This is Im over over the square root of 2 at a phase angle of at theta sub I, I'm sorry. So all I'm doing here is I'm now converting those magnitudes from RMS to our original Vm and Im. Well, if we define it this way, then I can look up at here. Note, SL is equal to 1/2 VL times IL. Why don't I simply define this with those RMS phasors? So therefore, complex power can also be expressed as an RMS voltage phasor times the complex conjugate of the IRMS, the current phasor, the IRMS value of the complex conjugate of the current phasor. What do I get out of this? I get the same answer as I would get up here, except now I've dropped that 1/2. And of course, that's what an RMS or an effective value does. It basically eliminates that 1/2 term from all of our power equations. Okay? Given this, let's apply this definition to the same example. I'm going to go ahead and I'm going to do a little bit of recalculation. What I'm going to do is I'm going to take this source and I'm going to convert this source to RMS form. So in this case, I'm going to take 150 and divide it by the square root of 2, which will be equal to 106.1. And so I'm going to write this as 106.1 at a phase angle of 0 volts RMS. And notice the units. This is an RMS voltage is what we're indicating here. So I've taken the original phasor and simply divided the magnitude by the square root of 2, which is what we'd expect for a sinusoid. Well, now that I've got this in rectangular form, this will just be equal to 106.1 volts RMS. Now let's go through and I'm going to calculate all of my quantities. Since my source is in RMS, all of the other voltages and currents in the circuit will also be RMS. So what I'm going to find is the impedance does not change. That stays exactly the same. But what I will get is the following. IL will now be equal to 106.1 divided by ZL plus 50. And using the same value of impedance I had before, this gives me 0.1892 minus J 0.4445 amps RMS. So that's an RMS voltage. I get an RMS current. And VL, the voltage across the load, is now equal to IL times ZL will be equal to 96.60 plus J 22.22 volts. RMS. And now I can just plug into the RMS complex power equation. And so now SL is equal to VL RMS times IL RMS complex conjugate. And I go ahead and plug those numbers in, and what I will get, not surprisingly, is 8.4 plus J, 47.1 volt amperes, which is exactly the same answer I got here. In fact, I'd be surprised if it was different. So what I've done here is, by converting my source to RMS, I no longer have to worry about the 1/2 term. Everything now just becomes S is equal to V times I complex conjugate in RMS form. And of course, when we're talking about power, power distribution, power generation, like from the electric company, this is another reason why we use RMS values. We calculate everything with RMS phasors. We do not have to worry about the 1/2 multiplier. Okay? So, important thing to remember. Remember, if the sources, the independent sources in the circuit, are specified in RMS form, all of the voltages and currents in the circuit will also be in RMS form. So, if the sources are RMS, everything is RMS. Impedances don't change, and impedance is not a voltage or current phasor. So impedance is going to be exactly the same, but voltages and currents will be in RMS form. Now, this actually tells you a bit of a strategy. When you're calculating complex power, if you don't want to deal with the 1/2 multiplier, if you don't want to do this, S is equal to 1/2 V times I complex conjugate, the first thing you can do is just convert your phasors to RMS form. So it becomes now VRMS times IRMS complex conjugate. And so when solving an AC power problem, convert the sources to RMS first, and you don't have to worry about the 1/2 term. Just go ahead and calculate it out. So if a source is not given in RMS form, you can convert it to RMS form before solving the circuit. So this is generally a good strategy. Most people just like to operate in RMS when they're using complex power. And so look at the sources. If you don't see the VRMS units, then it's not in RMS form, but you can convert it to RMS form just by dividing the magnitudes by square root of 2. And after that, you just use the RMS form of complex power. All right, so here's your introduction to complex power. And once again, this is the equation you want to use. You really don't want to use the earlier equation to calculate average power, because average power comes right out of the complex power whenever you go ahead and calculate it. Do this instead. Then you can just go through and use the phasor voltages and currents you're already calculating. All right? So next time we will look at the concepts of apparent power and power factor. And these actually fall right out of this equation, and I'll show you that next time.